Very much, and thank all of you for joining us today on today's part 3 of 100% outside air systems, where we look at passive radiant heating and cooling systems. This is the third part of a 3-part 100% outside air series that we have provided, and I think that due to various pressures that we're going to see perhaps more opportunities to use this type of system concept. My name is Dan Hani. Most of you already know me. Today's presentation is somewhat dense. If you want to look at credentials or whatever, don't hesitate to reach out to LinkedIn or whatever. I will say that I'm pleased to say that ES Magazine will be publishing this December an article on this very topic that I co-authored with Darren Alexander of TWA Panel Systems. So if you want to explore in greater depth and detail the topics that we cover today, I invite you to look at ES Magazine's website and pull the most recent article. Everybody knows Thermair Systems, who we are and what we do. To save time, we're going to bypass all of this. Other than I want to bring to your attention in our ambition and goal to stay attuned of what's developing in the industry and the market. Varitec hosted our first indoor environmental quality symposium. We were pleased to have Dr. Stephanie Taylor, one of the leading authorities on the topic, present here at Varitec on IEQ, and Dr. Mark Arith of Mayo Clinic presenting on contaminants and how indoor air quality and the environment infects human pathology. This is a growing initiative in the industry, and I'll make you more aware of that here shortly. Today's agenda, however, we're going to, first of all, assess what are the various pressures that are going to be influencing how HVAC systems are designed in the future. We're going to discuss briefly the White House indoor air quality initiatives that they've launched. We're going to look at, we're going to review our previous couple of sessions on what are the modes of heat transfer, conventional versus what if. We're going to look at passive radiant cooling and heating theory and concept. We're going to look at thermally stratified environments briefly and how the air side component works with a passive radiant solution. We're going to look at various types of products that are used, radiant products that are used for applying the application. And then we're going to look at some design considerations, and if time permits, how is the DOAS unit configured for 100% outside air passive systems? So first of all, let's begin. What are the most recent initiatives regarding indoor air quality? The White House on October 11th held its first indoor air quality summit. Its goal was to bring to national attention the Biden administration's plan to manage COVID-19 and other infectious diseases as well more effectively by drawing attention to the importance of indoor air quality. On October 10th, the White House hosted the summit on this very topic of indoor air quality and launched its Clean Air in Buildings Challenge. And there's a website the White House has initiated to support this. The White House leaned on ASHRAE, and there's a dialogue that's opened up between the White House and ASHRAE in getting the information necessary from ASHRAE on how to create better IAQ in the environment. So the Clean Air in Buildings Challenge was promoted, and the challenge's goal was to have the quality and cleanliness of air breathed in a building every day, make people aware that the air that we do breathe has a significant impact on our health and well-being. And the better the indoor air quality, the more we can maintain a healthy indoor air quality, we can actually reduce the number of infectious diseases such as COVID-19, which is its primary focus, but now RSV and flu. my daughter-in-law, my future daughter-in-law, was in the hospital the other day, and she had to spend her 4 days in the ER because they were out of beds. So infectious disease and the pandemic is still influencing our healthcare system. So the government is moving and taking action to bring about greater public awareness on how indoor air quality can reduce the risk of infection. The Clean Air in Buildings Challenge is a call to action for organizational leaders and building owners, operators, to assess their indoor air quality and make ventilation, air filtration, and air cleaning improvements to help keep occupants safe. There were 4 commitments owners would need to assign themselves to if they accept the challenge, and I wanted to bring to your attention commitment number 2, which is optimize fresh air ventilation. In other words, bringing clean outdoor air indoors and circulate it when it is safe to do so. So the federal government and ASHRAE have all acknowledged in their various ways that bringing outside air into a space, at least in conformance to minimum requirements by ASHRAE Standard 62.1, is necessary to reduce the risk of infection, but all of them advocate that if you increase the outside air beyond minimum, that it offers an even better solution. Well, the CDC argues as well that when indoors, ventilation mitigation strategies can help reduce viral particle concentration. And consequently, it says open outdoor air dampers beyond minimum settings to reduce or eliminate HVAC recirculation. The EPA has this statement: the primary causes of indoor air quality problems is due to inadequate ventilation, and it advocates for increasing ventilation rates to reduce the amount of contaminants or concentration of contaminants in the space. So again, the EPA states an important approach to lowering the concentrations of indoor air pollutants is related to the amount of outdoor air coming indoors. There might be a concern that, well, what about the outdoor air quality in large municipal areas such as downtown Phoenix, especially in our colder winter months? The actual fact of the matter is that indoor air quality is still poorer than the outdoor air quality, for the very simple reason that indoors you not only have the various compounds that are off-gassing within the space and all the particulates that gather within that building, but if the building is getting the outside air that it needs, then it is also introducing the outdoor air pollutants into the space. Consequently, the EPA's website makes the statement that their studies have shown that human exposure to air pollutants indicate the indoor levels of pollutants may be 2 to 5 times and occasionally more than 100 times higher than outdoor air levels. So that's a pretty useful piece of information in considering the application of 100% outside air systems. And there's another component that's gaining national attention as well, and that is CO2 contaminant levels. How much CO2 is in a building? ASHRAE has always advocated for 1,000 parts per million of CO2 per cubic foot of air. However, we're finding out now that as outdoor CO2 concentrations increase from about 360 to 380 parts per million as were measured back in the 1980s, they're now measuring in the range of 500 to 600 parts per million here in Phoenix, Arizona, downtown, and in Los Angeles from 600 to 700. So if you adopt ASHRAE 62.1, 700 parts per million delta between indoor to outdoor as a baseline for indoor concentrations, you're now seeing concentrations in the realm of 1,200 parts per million, 1,300 parts per million. And recent studies have demonstrated that cognitive facilities can be impacted by CO2 concentrations of 1,000 parts per million. So there's a push now occurring in the background advocating for CO2 levels of between 600 to 800 parts per million. The only way you can do that is increase your outside air. So let's go ahead and do a quick review of what we've covered in the last two sessions. That revolves around the modes of heat transfer, and we're going to evaluate conventional versus what if. So in review, what is the purpose of an HVAC system? It's to maintain thermal comfort and indoor air quality. How do HVAC systems do that? By moving air and energy from or to a building. So how do we actually condition a building to maintain thermal comfort? Well, we have to calculate the amount of heat load that occurs within the building or leaves the building in winter, and make sure that we remove the energy that's added to the building so we can keep a thermostat at a set point, or how much energy we need to add to a building in winter to keep a thermostat set point. The total energy is comprised of two energy types. One is sensible energy and one is latent energy. And the total energy that accrues in a building or becomes absent in a building in winter can be added or subtracted by four modes of heat transfer. In the whole realm of physics, there are only four modes of heat transfer that we are aware of. They are conduction, convection, evaporation, and radiation. So a quick review from our last seminar, I would like to look at what sensible heat energy is. Sensible heat energy is the heat that a person senses. It is the energy measured also at the thermostat, displayed at the thermostat, and is also referenced as the dry bulb temperature. The other form of energy is latent energy. Latent energy is the amount of energy required to maintain water in a vapor state. You remove enough energy, any water in the air will condense into a liquid and condense out of the air as rain or droplets or dew, etc. Latent heat is referenced as wet bulb temperature, and it's in Fahrenheit. So you have dry bulb and wet bulb temperature impacting both thermal energy or heat energy and energy required to keep water in a vapor state. These two items need to be addressed to condition a building. In a conventional heat transfer mode, an all-air system, total building load is present at an air handler or a package DX unit coil. It's either a cooling or a heating coil. And we also talked about 1 ton of energy of load, total energy, which is sensible plus latent energy, is equal to 12,000 BTUs of energy. So in a conventional system, if we want to move energy from a building to outdoors in cooling, air becomes the heat transfer medium. We cool the air at a low enough temperature to remove and supply it to a building to remove the heat gain in that building. Or in heating mode, warm the supply air temperature up to a degree that we add the heat to the building that was lost due to the cold outdoor environment. The problem is that if air is used as the heat transfer medium, air is not very dense, so it can only hold 0.46 BTUs of energy per pound of air. So in order to move heat or add heat to a building, you need to move a lot of air. Consequently, you have to use fan horsepower to do that. Conventional all-air systems then condition a building by moving air throughout the building. And the two modes of heat transfer that applies are mechanically forced. They are evaporation. When I was growing up in Phoenix, Arizona, a number of years ago, many homes had direct evap coolers. Evaporation is one mode of heat transfer because to transition water from a liquid state to a vapor state, that moisture absorbs energy so that water can exist in a vapor state. The other form of evaporation occurs in the vapor compression cycle, either at refrigerant compressors in a packaged DX unit on a roof or from chillers. It is by the control of pressure that you control the evaporation, and condensation rates of refrigerant, thereby creating the heat transfer solution of a compressorized unit. The other mode of heat transfer is conduction. Heat transfer that occurs through heating and cooling coils where air comes into direct contact with a chilled or warm surface, allowing for energy to either be removed from an airstream in cooling or added to an airstream in heating. From a room side standpoint, a conditioned space, we actually condition the space by creating a mixed air environment. We condition the cubic volume of space. It's recommended by ASHRAE you maintain plus or minus 2 degrees of temperature set point throughout the cubic volume of space. And we roughly see that at about 75 degrees dry bulb, 50% RH. 50% RH is certainly a condition we can achieve here in Phoenix, Arizona during our monsoon months. And we condition that space by providing 55-degree supply air optimally. Fact of the matter is, many of our packaged DX units don't even achieve 55 degrees, and we want to achieve 55 degrees to wring moisture out of the air, the mixed air condition the coil sees, so we can hopefully control building humidity levels. That air is injected at high velocity into a room at 150 feet per minute to create a thoroughly mixed environment. So you want to make sure that the air within the space is thoroughly mixed within plus or minus 2 degrees. To do that effectively, a 20-degree delta T is required. It is a 20-degree temperature differential between the air entering a room at 55 and a room set point at 75 degrees. And this 20-degree delta T, I ask that you keep in mind for later in this presentation, because you're going to see the difference of what passive radiant solutions offer by using chilled water as the heat transfer medium. So instead of a conventional system, what if we rethink the modes of heat transfer that we have historically and traditionally applied? What if we exploit all 4 modes of heat transfer? We would still use the mechanically forced heat transfer modes of conduction and evaporation, either through air handler cooling coils or chiller vapor compression cycles. But what if we take a passive approach to heat transfer? What if we let the forces of nature take on some of the work that is necessary to move energy from a building? The other 2 modes of heat transfer are convection, warm air rises, cold air falls, and radiation. Radiation is heat transfer energy in the form of electromagnetic waves. So what if we exploit all 4 modes of heat transfer? Well, a passive radiant cooling and heating system does offer such a solution. So here's how the concept works. So how do we do that? How do we exploit all 4 modes of heat transfer? We apply a decoupled passive hydronic 100% outside air system. We already know that outside air is a good thing for a building. We already know that the government and ASHRAE are advocating for more outside air for reasons expressed in technical papers and etc. So it seems to make sense that we perhaps use that as a design strategy. So let's look at it though in detail and build the argument as to why it makes sense. So instead of the total load being seen at a cooling coil in an air handler mounted on the roof, what if we decouple the total load into its sensible and latent components? What if water becomes the heat transfer medium for the sensible load? What if you remove or add sensible energy local to each zone and not air? Well, why would you want to do that, and what advantage does it hold? Well, water, because it is a more dense heat transfer medium, has 3,300 times more heat carrying capacity than air. How is that? Well, air can hold, as I mentioned earlier, 0.46 BTUs per pound of air. Water can hold 8.98 BTUs per pound of water. Why? Because water is more dense than air. So why would we do that? Well, less water would be required to move the same amount of sensible energy from the building. Why? Well, less heat transfer medium means that using water as opposed to air would mean less ductwork. Less ductwork results in reduced fan energy required to condition a building. Less fan energy results in reduced horsepower. Less horsepower, pumping horsepower versus fan horsepower, and consequently buildings historically that apply passive 100% outside air systems are seeing 20 to 40% energy reduction. And I have heard through a case study Price Industries actually initiated about 8 years ago of a retrofit school that actually saw 50% energy savings over the projected. So over a conventional design. So anyway, why are these systems then more efficient? Because they exploit parts of the physical laws of heat transfer by using a more dense heat transfer medium, and by exploiting the passive heat transfer modes of radiation and convection. There are other benefits other than the energy component as well. There's improved thermal comfort, which we're going to explore. 100% outside air systems have been known to provide better IAQ, and the same amount of energy can be moved from a building with less work. So again, to review the system concept, a passive system works with the sensible load moved to chilled water loop through radiant panels and sails located in the conditioned space. Ventilation and humidity control is parallel to and decoupled from the passive radiant system. It is your 100% outside air unit that will control the humidity in the space by supplying air at an adequate enough dew point to absorb the moisture buildup in that building. So the airside component uses a 100% outside air unit. There's no return air back to the building. Airflow is now designed as to about 0.3 to 0.8 CFM per square foot of a building versus 1 CFM to 1.1, 1.2, depending on your geographical locations and your peak load conditions. Building humidity, your latent load is controlled by supplying the outside air at a low enough dew point so that the incoming air absorbs the moisture buildup in the space. So the 4 modes of heat transfer that we're putting to work, we're going to let the physical laws go to work for us, are the mechanically forced heat transfer modes of fan energy, and then we're going to look at, of conduction, and then of evaporation, and then we're going to exploit the forces of equilibrium sought by imbalances of energy through radiation or air temperature through the forces of convection. So let's look at the passive heat transfer modes. Let's look at radiation. Radiation is energy heat transfer in the form of the electromagnetic spectrum. We all experience it every day we walk outside and are exposed to the sun. It is infrared energy specifically that we're dealing with. And we actually use radiant heat transfer by creating an imbalance of energy of surfaces within a space. We either chill the ceilings to absorb heat energy from surfaces in a space, or heat ceilings or walls perhaps, in order to add radiant energy to a space. When you use this mode of heat transfer, fan energy is not required to move energy. It was by creating an imbalance of energy levels within the local zone, within the space, that allows for heat transfer to occur. In a passive heat transfer mode for exploiting radiation and convection, one of the solutions is the use of radiant panels. These are metal surfaces that reside in the ceiling. In fact, they can actually compose a ceiling in their actual design. And by cooling a ceiling, you actually absorb warm temperatures or energy emitted from warm surfaces within that space into that cooled surface. So consequently, radiant systems are conducive to better thermal comfort because an occupant's emitted thermal energy is actually absorbed within the surface of the chilled ceiling. The other option is to heat the ceiling in wintertime at an adequate temperature so you can emit the radiant energy to heat surfaces within that space. A typical panel capacity in cooling is 25 to 30 BTUs per square foot, and in heating it's 100 to 200 BTUs per square foot. There is also a convective effect. Due to conduction, air close to the panels are cooled, and consequently, if that air is cooler than the ambient room condition, it'll fall to the floor via convection. And so the convective component of a chilled ceiling is responsible to 30 to 40% of the cooling within that space. So it is both radiant as well as convective. You don't have a convective heat effect because the warm air will stay in the upper levels of the room due to thermal buoyancy. The other type of product that's available for passive radiant technology are radiant sails. They are louvered devices that enhance the convective effect. They allow air to pass through them. And the actual radiant component are louvered fins that are assembled together in rectangular or custom arrays that not only emit radiant energy from a warm surface or absorb space-side room energy by creating a cooler surface, they will also allow air to more freely pass through the device through the forces of convection. So consequently, the convective to radiant effect on a sail is about 50-50. And so a radiant sail can provide 40 to 55 BTUs per square foot of sail in cooling, and heating up to 80 to 200 BTUs per square foot. So radiant energy is emitted or absorbed by the louvered blades within the sail. Cool air around the chilled sail blades fall via convective forces to the floor. And in order to mount these sails appropriately, you need to make sure you have an adequate space between the top of the sail and the deck or surface you're suspending it from, so air can freely move up behind the sail and drop back down through the louvered fins back into the occupied zone. So how do we make sure that we get maximum heat transfer at a radiant device mounted in a ceiling? Well, you want to make sure you maximize the temperature differential of the room air adjacent to that panel or sail. And to do that, you create a thermally stratified environment. By creating a greater delta T at the radiant panel or sail, you actually allow for more sensible heat transfer at that device and a greater force of convection. So thermally stratified environments are optimal for getting the most effective use out of a passive radiant solution. So what are thermally stratified environments? And how do we design the airside factor for a passive radiant system? First of all, what is thermal stratification? A thermally stratified body is one that has a temperature differential throughout the body, whether it's a frying pan on a kitchen stove where the pan itself is exposed to an open flame and that heat that is absorbed into the metal is actually transferred down the handle of the pan, or whether it's a lake effect in the summer months. The radiant heat from the sun is absorbed by the surface water to a certain depth. However, when you go deeper into that lake water, it gets colder and colder and colder. So, because the radiant effect cannot penetrate that deeply into the water. Well, if we take the thermally stratified concept and apply it to a room air environment, what actually occurs? Or how do we create that environment? Well, unlike a mixed air system where we inject air at 150 feet per minute or at high velocity through diffusers or sidewall registers to encourage and increase mixing, we actually inject air at low velocity into space through devices that are hung low in wall called displacement diffusers, or through an underfloor air system where the diffusers are mounted in the floor, served by air that from a plenum beneath the surface of the floor. Air is injected at about 40 feet per minute. Supply air temperature is 62 to 68 degrees versus 55 degrees in a mixed air system. Why? Well, you don't want to have too cold of air too low on the floor, or people experience cold feet and cold ankles. If you create a condition of, if you supply air at 65 degrees at low velocity to maintain a room at 75 degrees, the thermally stratified profile looks like this. The floor temperature is about 70 degrees. The ceiling temperature is about 78 to 82 degrees for a 9-foot ceiling. So consequently, you have a thermal profile in the space that maximizes the delta T at the radiant device. The upper room levels can see up to 80 to 85 degrees where the air is exhausted from a building. And the elegant fact of a 100% outside air passive system is that air is not only exhausted from a room that is brought then back to an air handler where it mixes with outdoor air, is conditioned at the coil and re-injected back in the building. 100% outside air systems exhaust the building air from the building. There is no return air path of building air into the space, which is one of the reasons why it is very promising for creating an environment with superior indoor air quality. So what drives air in the space if it's not fan energy injecting air at high velocity? Heat. Heat sources in the space are the source for moving air. Consequently, where you have an occupant of 98 degrees and the space set point is 75, that warm occupant has a vertically rising thermal plume of roughly 30 feet per minute that is carrying clean, conditioned air across the breathing zone as warm, contaminated air is transferred to the upper levels of the room, where it is exhausted not only from the space, but from the building. Consequently, a thermally stratified environment promotes clean, cool, conditioned air across the breathing zone, as opposed to a mixed air system, which is doing its job, that should somebody be sick in a room and they cough or sneeze or even tidal breathing, will eject virally loaded droplets within the space. The mixed air system is doing its job by thoroughly mixing that contaminant throughout the space. A thermally stratified environment discourages to some extent that phenomena, allowing for better IAQ and can reduce the risk of infection. ASHRAE recognizes better IAQ for buildings that use displacement ventilation. If a building is being designed with this technology, it can apply a 1.2 zone air distribution effectiveness, which means that you can reduce your outdoor air levels by 20%, which you may or may not want to do depending on what the owner is looking for in the building, but that opportunity is there. And the reason why I included this slide specifically was to demonstrate ASHRAE's recognition of displacement ventilation and thermally stratified environments as being conducive for creating better IAQ. So how do we calculate the air side, and how do we determine whether or not passive radiant 100% outside air systems make sense? Well, what we need to do in designing the air side is make sure that we define how much air is required for a room and for a building to comply with ASHRAE Standard 62.1's minimum ventilation requirements. And then you apply an air side load fraction rate. That is the amount of sensible energy removed from the space by bringing in the supply air temperature at 62 to 65 degrees through a displacement diffuser and assigning how much sensible load is met with that air side. Once that is determined, you can then begin to size the radiant component. How many square feet of radiant panel or active radiant panel or active sail are required to satisfactorily meet the remaining sensible load. Lower airside load fractions demonstrate and argue for a more effective use of passive radiant technologies. If you have an ALF value that is less than 1, then it makes all the sense in the world to evaluate it for using it in a building design. If it's greater than 1, then there's too much air required in the space to make sense of using passive radiant technology. From experience and because of the actual ventilation rate requirements for offices, classrooms, and lobbies, if you look at the airside load fraction rate for an office, it's at 15%. Offices, therefore, make all the sense in the world for applying passive radiant technologies. Classrooms, 33%. Lobbies even at 50%. So with this calculation, you can begin to assess whether or not passive radiant systems make sense for a design, make sense for the various zones within a building, and maybe a zone that would not make sense to apply it for by calculating what that airside load fraction value is. And by reducing the amount of air supplied to a building, allowing heat transfer to take place on the chill water loop, you can reduce fan energy significantly. And it's not uncommon to see 35 to 40% reduction of energy due to a reduction of horsepower necessary to move energy to and from a building. I will say that when I worked with the GLHN team out at Tucson in laying out the University of Arizona Environmental Natural Resource Building, I believe that's what it is, the ENR building. One of the first comments that Henry Johnston made from GLHN was, "Dan, where did all my airflow go?" He was able to design his airflow rates to 0.25 to 0.35, 0.4 in a couple of zones because of how those zones were used. So he saw the radical reduction of that, of using a passive design. Not to mention, that building secured for GLHN, as I understand, 2 years ago, the Energy Savings Award from ASHRAE. So we were really excited about that realization. So room airflow rates, calculations, and conditions. How do we know how much air to bring into the space? Well, first of all, we need to make sure that we meet the minimum ventilation requirements per ASHRAE 62. We need to apply psychrometrics to remove 100% of all latent loads within the building because the outside air is your humidity control factor. We need to make sure we have enough airflow to maintain building static pressure of 0.01 inches positive, and then to handle any supplemental sensible loads for zones with higher ALFs. Whichever is greatest of these factors will set the minimum airflow rate to a building. So that is a good guideline to understand how much airflow you should use. Dedicated outdoor air units, however, need to be laid out a little differently. They need to be laid out so they can provide a high enough leaving air temperature of 62 to 68 degrees while also dehumidifying the air adequately. So how do you do that? Well, the air off the cooling coil has to see a low enough temperature to create the dew point depression necessary to control building humidity. And that's an easy enough calculation to do. So in order to calculate and assess the humidity infiltration, we need to be aware of what is the moisture infiltration through perimeter walls. What about doors opening and closing to the outdoors, especially during our wettest times of the year? What about bathrooms, sinks, kitchen sink infiltration, etc.? Anywhere where there's exposed moisture in a space. And I will add, if you have a building with fan coil units and condensing fan coil units with drain pans, those drain pans have exposed water into the base in their have drain pans filled with water that are exposed to the air within the building. So they do become a humidity factor within a building as well. So we need to make sure that we maintain dew point control within a space. We need to provide 100% of the latent load under peak Arizona design conditions for buildings located here. And we also need to take into account what the maximum occupancy is per zone. So you do have to be aware that you prevent overcooling in spaces by keeping air fraction rates low. You want to have temperature reset strategies for the appropriate conditions in order to enhance efficiency. You want to look at chill water supply shutoff and entering water reset in the event humidity does become an issue in a space for whatever reason. And then, of course, you want to have VAV control for zones that see wide swings of occupancy within that space. So passive radiant cooling and heating panels and sails, what are these devices? Well, these are, again, thermally activated panels or louvered sails that reside in the ceiling or possibly for panels in a wall that are thermally activated. They are made out of aluminum extrusions, especially for sails, aluminum sheet metal for panels. They can be made out of steel, and they can be made in custom configurations. Along the back of these sheet metal pans or louvered sails are serpentine coils that are placed and adhered on saddles with thermally conducive paint or adhesive, so that we maximize the heat from the coil through to the surface of the panel. Another thing to keep in mind is the acoustical performance of the panel and whether or not they need to have supplemental insulation on the back to maintain adequate sound within a space. Panels can be castellated, that is to say grooved or ribbed. They can come smooth, they can come in many architectural features, so they can be architecturally friendly. The first passive radiant job I was involved with was with Bridges and Paxton, I think in 2009 for a City of Phoenix project, when they got the costs in of just going with a radiant passive inactive ceiling in lieu of an architectural ceiling with radiant devices mounted in it. It became more cost effective to do the whole ceiling. So something to consider, and you can get there are a lot of different styles and designs available with radiant ceilings that an architect might want to consider for their building. Radiant panels can actually fit in tegular or T-bar grids. They can come in linear or curved options. They can make radiant clouds within a space as well as an architectural feature that actually lends itself to the HVAC system. You can provide these devices in secure environments as well. One of the things you want to make sure that if you're designing to it, that you have the proper independent testing and standard for these devices to secure confidence that the manufactured product has the heat transfer that it proposes to have. So looking at radiant sail products, again, these are louvered blade devices made of extruded aluminum. They are high capacity devices, and they offer more heat transfer capacity. These are located predominantly at the perimeter of a building where they can absorb that radiant heat effect in the summertime off of a perimeter wall, as well as provide a convective flow of cool air back into the space. There are many different types of paints available, different types of louvered designs available, and there is also a high capacity design known as the Q-sale to maximize the BTUs per square foot of sale. Radiant devices can also come in the form of light shelves right at the perimeter window. These devices are conducive for optimizing illumination within a space by reflecting light off the top and off the bottom back into the space, while also serving as a sensible cooling and/or heating device at the perimeter to reduce the radiant effect off of perimeter walls. So, what are some passive radiant design considerations? Well, let's look at the water side design factors. Now that we've looked at some of the preliminary air side factors, we need to ask ourselves the question about the water side. Well, we need to determine what the water flow rate is to be to each zone. We need to determine the pressure drop that is available. We need to determine the temperatures of the water and of the room being served by the system. So what is the entering water temperature and the leaving water temperature? The sensible load design parameters have to be done, again, as a reminder in relation to how much sensible cooling is achieved by the ventilation or outside air factor. And then, of course, the sail and panels are designed accordingly in respect of that. So, looking at radiant cooling from a water standpoint, entering water is typically between 56 and 62 degrees. You don't want 44-degree chill water in a space, because that is far below space dew point of 55 if the room is conditioned to 75-50% RH. So you want warmer chill water, 56 to 62 degrees. Providing 56 to 62 degree chill water will give you about a 4 to 6 degree delta T of your chill water. That's quite a difference from the 20 degree delta T you need on an all air solution. You want to supply your entering water at 3 to 4 degrees above space dew point, because you don't want the panels or sails to condense. And that's easy enough to do, providing you have confidence in assigning the dew point temperatures to a space, which will be 55 degrees in a space designed to 75 degrees, 50% RH. In heating, the entering water temperature will be between 120 to 180 degrees. Usually we see about 110 to 120, 130 in the lower temperature range. And then the delta T is greater in heating mode of 10 to 30 degrees versus 3 to 4 degrees in cooling. You want to make sure that your minimum flow rate per circuit is about 0.65 GPM. You need that amount of flow as a minimum to attain the heat transfer capacity out of the device by providing sufficient turbulent flow throughout the tubing so that you maximize heat transfer through the coil. Some design considerations on the water side. Make sure that the chill water system has a hot water system has a variable speed pump design, so you're maintaining the proper fluid flow rates throughout the building at all points, and you can use a variable speed pump to do that, to maintain the actual water side pressures necessary to get adequate flow to each of the devices in each of the zones. There are various piping options. There's a direct return option. Length of pipe varies from the supply header to the return header for each unit. There's a change in pressure drop from one circuit to another, affecting flows. And you need to use a balancing valve and a circuit setter appropriately to the zone load in order to make sure that water is adequately distributed throughout the array of devices that are being used. There's reverse return, which is recommended solution. A reverse return piping configuration is first connection supplied, last connection returned. The zone or array is self-balancing. The number of valves in a space can be reduced. However, it does require more piping. So it's sort of a rob Peter to pay Paul with regard to added or decreased cost depending on the valving and the copper piping, etc. Another piping solution is series piping, but you have to be very careful about series piping because the furthest device from the entering water is going to have the least capacity as that chill water is absorbing the energy of that space. So there may be an application for it because it has some advantages in specific environments, but realize the total capacity loss throughout that array in a series configuration. We advocate more for parallel piping configuration. These are especially used with large panel arrays connecting several sets of panels in series. You have reduced pressure loss in this configuration, lower flow rates to achieve the delta T you need, and a much better temperature distribution throughout the surface area of the devices. There are 3 waterside design concerns with a passive radiant system. Use of glycol as an operating fluid, especially in cooling, not a good idea. Not considering the use of pressure-independent flow control valves. Valves that can always assure that the necessary water is getting to the radiant component regardless of fluid pressures within the piping scheme. And then, of course, valve and entrapped air noise you need to be aware of and how to address that. That can be addressed in the actual design of the water system and taken care of. So lastly, we're going to look at the airside component again and what is involved in the designing and layout of displacement ventilation 100% outside air units. First of all, again, I'm going to go back to the point that we need to make sure that when you're designing to a 65-degree supply air temperature, you're actually providing air at a low enough dew point to control humidity in the building. Consequently, the chill water coil of the DOAS needs to be designed so that it achieves low enough dew point to adequately control humidity within the space. Here's a design of a configuration we used with a displacement system in a Banner Boswell Medical Center. I don't know that I would recommend this configuration in a 100% outside air system. This is uses a property called side stream bypass, where mixed air is injected into the supply air stream after the cooling coil as well. There's a damper and a bypass section that modulates open and close to maintain a leaving air temperature out of the air handler, 62, 65 degrees, since the mixed air condition is perhaps about 80 degrees, 80 to 85 degrees, certainly in cooling. And then you provide your adequate dehumidification at the cooling coil and then reheat it without using additional energy by mixing that mixed air into that supply airstream. Another option is to use a dual wheel 100% outside air unit, one that uses an enthalpy wheel to precondition the outside air both for sensible and latent heat. That preconditioned air then passes through the cooling coil, and there's a secondary sensible only heat wheel that transfer the energy from the room into the supply air stream to add another 5 to 10 degrees of temperature to the air coming off the coil, so we can supply 62 to 65 degrees of air that is properly dehumidified. Another solution that should be given every consideration, in my opinion, is looking at a custom packaged DX solution. Now with our variable speed compressor technology, our ability to modulate refrigerant flow based on demand, the capacities to provide suppressed dew points of 48 degrees, 46 degrees, make this a very attractive option for future building designs. And by using hot gas reheat technology in a DX 100% outside air unit, you can control the leaving air temperature after dehumidifying air at the chill water coil by using the heat of rejection off of a compressor and allow that heat to pass through a bypass, hot gas reheat coil that will post-heat the air off the chill water coil without using any other form of supplemental heat. You've already paid for the energy in the cooling cycle, so you can use that to post-heat the supply air to your assigned 62 to 65 degrees. If you take advantage of the DX option, there are some other advantages as well. You can start looking at air-cooled chiller technologies. That makes sense, especially in Arizona, now that we're challenged by our drought and the lowering of amount of available water that's becoming present to the southwest. We did a study in comparative analysis using Daikin's new Pathfinder chiller, comparing how that chiller performs supplying 44-degree chill water that is used in a conventional HVAC system for dehumidification at air handler coils. And we laid out a configuration with 18 condenser fans, and the actual performance review showed that supplying 44-degree chill water results in efficiency of 8 EER and 21.3 IPLV. However, if you're able to supply 55-degree chill water, your EER jumps now to 10.6, your IPLV to 22.2, making this an excellent solution for adding another layer of efficiency to an HVAC system if you're using a DX 100% outside air solution that uses compressorized energy. You don't have to worry about a primary, secondary pumping loop. A conventional passive hydronic system would require, because you would need to provide 44-degree chill water to a DOAS unit for adequate dehumidification, preferably probably less to get to the dew points necessary. But if you provide a DX DOAS solution, you can elevate your chiller chill water temperature to 55 degrees, adding another layer of efficiency to a passive radiant system. So quickly and in review, now that we've reached our time in this presentation, we've reviewed the recent initiatives from the federal government, from the White House, in beginning to address the importance of indoor air quality in a space. We did a quick review of HVAC systems and the modes of heat transfer. We looked at conventional versus what if, or 100% outside air passive radiant designs. We looked at the theory and concept of passive radiant cooling and heating. We looked at thermally stratified environments necessary to optimize performance of a passive system. We looked at the various panels and sails and components available for passive radiant systems, and some waterside design considerations, and a couple of quick references to 100% outside air units that could be considered. So with that, please, are there any questions?
There are no questions in the chat currently. So if anybody does have any questions, you can either unmute yourself and ask or put them in the chat. Well,
Nothing's coming up?
Nothing's coming up.
Okay.
Yes, I will be sending out a link to the presentation along with the recording. It'll be on our website probably by the end of next week. Was somebody going to ask a question? Okay, we have a question, Dan. Any thoughts on using radiant panels on return side with a standard chiller system?
I Absolutely. It all depends on what is that entering water condition. I don't know why you couldn't. You figure you've got in a conventional chiller system, 44-degree chill water with 54 return. If you have the means of maybe making sure that the space conditioned has a low enough dew point where 54-degree chill water will not cause the panels to condense, that might work. But if you do have that room, we would have to have a solution for picking up another few degrees in that chill water so that condensation doesn't occur.
Okay, so we have another question from Matt. Do you have any other recommendations to address IAQ like UV or ionization?
Absolutely. We live really in a fluid world right now. We don't know what's going to happen with the pandemic. We don't understand how mutations could impact the virility of the viruses that are available to us. So as ASHRAE advocates for, in its reference to Standard 170 and using a blended approach for reducing the risk of infection, being able to layer solutions such as UV lighting or for ionization or for the type of distribution you might have in the space, or as Dr. Kishar Kaharni wrote an article in the ASHRAE Journal of July of 2021, I believe it was, on as simply as how you locate or how many return grills and supply grills you put in a space to more effectively push room air to the return grill than a conventional layout. Any of these solutions will only increase your will improve your indoor air quality and reduce the risk of infection. There's a consideration, of course, with using energy recovery enthalpy wheels in during the period of pandemic, and that can be easily resolved by putting a UV light before the chill water coil downstream of the enthalpy wheel to make sure that any released pathogen back into the airstream can be adequately dealt with. It just adds a layer of protection. Providing ionization, certainly, we're finding can be very effective, especially if it can be brought very close to the zone itself. Variable refrigerant systems are very conducive for doing that with devices that can be mounted directly in the air handlers or fan coil units located in the zones. So yes, another consideration as well is proper humidity. That is a very important factor in environmental or indoor environmental quality. Indoor environment actually can maintain, can reduce the risk of infection and create a healthier environment for occupants by maintaining humidity levels between 40 to 60%. ASHRAE's Epidemic Task Force is advocating for that as well. So the more measures that you can apply to reducing the risk of infection and to creating a healthier environment should all be considered, providing the budget is there to support it.
And I will add to that we have given webinars on all of those different topics, and we actually have all of them saved on our website. So when I send the link out next week, or you can go there now, it's under the resource library under the training tab. Is all separated by the different topics that we have done. So Dan has done one on ionization. He's done one on humidity, on UV lights. So you can go and watch the past videos. And if you ever want an updated and live webinar on any of those topics, just reach out to me or Dan and we can schedule something specific.
Absolutely. And for architects who are joining us, I've got like 10 presentations that are HSW credited.
Yep, I have a whole list.
So,
yep, 10 presentations.
So absolutely glad to support in any way we possibly can.
All right, so that wraps it up for the questions. If anybody does come up with any questions after we get off, you can always email me or Dan as well. All right, and thank you, Dan, and thank you everybody for joining us.
Kelly, thank you.